Hello, everyone. Thank you for joining us tonight for our stargazing lecture. I'm Dr. Cameron Hummels. I will be the host for tonight's event, as always. So a few announcements before we get started. Just first, the layout of tonight. I'll have a couple of announcements for a few minutes, and then I'll introduce our esteemed speaker who's going to talk all about supernovae and astronomical transients, as well as a really cool app that's been developed primarily by our speaker, so that people can play essentially an Android app to interact with this astronomical data, and it's effectively kind of like Pokemon Go, which is pretty cool. So he's going to talk all about that tonight. So that'll go on for about 30 minutes, and then we'll take a few questions from the audience for 5 to 10 minutes or so. And then we'll have kind of an intermission of about 5 minutes where we get set up, we bring this table out, and we have a Q&A panel consisting of our speaker, myself, and 2 other members of the department who work on different areas of research related to astronomical transients. And then while that Q&A panel is going, we'll also have telescopes set up now that it's starting to get dark enough that we can see things in the night sky. And that's on the fields just behind us. So at the end of the talk, I'll let you guys know where to go, but essentially you go out the front door and follow the signs just in the fields right behind me. It's about a 60, 90-second walk. And there are 3 telescopes being set up right now as we speak. And tonight we should be able to see probably the Ring Nebula. A beautiful moon is going to be up just after first quarter. And then there's actually a new comet that's coming into the inner solar system. It isn't super bright yet that you can see it with your naked eye, but it is expected to be bright enough that you can see with your naked eye in about a year, around March, April of 2024. It's called Comet 12P Pons-Brooks, and it's having an outburst of material that we might be able to see through one of the telescopes. So that should be cool as well. So these events happen once a month, typically on a Friday night. We've had quite a few in the last month, probably like 3 or 4 in the last month and a half, but we'll go back to our normal cadence next month. We're going to have an all Spanish language stargazing lecture that happens 3 weeks from tonight on August 18th. It'll be on the topic of stars. And again, if you don't speak Spanish, it's probably not worth coming. I'm not going to be here translating because my Spanish is an abomination. But for those of you who do speak Spanish, I encourage you to come and spread the word. We're putting out advertisements about it right now. That'll be given by Rocio Kimon, who's a postdoc in the department working on stars and the evolution of stars and planets around them. So that should be really cool. The next English language one of these will be the following Friday, the 24th, I think, and it'll be given by Emily Silich, who's a PhD student in the department working on clusters of galaxies and the collisions of these clusters of galaxies, which are essentially the largest explosions in the universe since the Big Bang, which is pretty sweet, right? So she'll be talking, and I'll put out all the posters and advertisements associated with these events, but I encourage you guys to come back. And in addition, we have an associated series called Astronomy on Tap that takes place at a bar in Old Town, Pasadena. It's a restaurant bar. It's called the Dog House. Perhaps you've been there. They serve food, they serve drinks, but we have a night once a month on a Monday night where you can come, perhaps order food, but you don't have to. You can just come for the science, which is free. And we have 2 speakers who give 15 to 20-minute talks about science in a less formal atmosphere than here in this, white ivory tower that we have here. And it's super fun. There's live music. We have astronomy-themed pub trivia, and there's telescopes at that, although the telescopes there aren't nearly as good as here because you're right underneath streetlights in Old Town, Pasadena. But it's super fun, and the next one of those will be Monday, August 14th, featuring a talk about cosmic neutrinos, these very lightweight particles that are traveling from distant places in the universe, and we can detect them with detectors here on the Earth. In fact, there was a big press conference a month ago about new neutrino detector and what it could discover essentially the Milky Way in these particles. And the other talk will be about the early universe as seen by something called 21 centimeter radiation, which is something that is observed with radio telescopes, and it tells us about the very early universe, earlier than you can pick up in other wavelengths of light, like with the James Webb Space Telescope or optical telescopes. This can pick up before galaxies and stars had even formed, which is pretty wild to think about. So those speakers will be talking about that. So enough of my rambling announcements. Our speaker tonight has been a member of this department for almost 25 years. He did his PhD in India, in Pune, and he's both a research scientist as well as the machine learning lead for the ZTF survey here, which he's going to talk about, which discovers kind of the changing night sky overhead. And oftentimes we think of the night sky as being this static thing, and you go out every night and it's the same, but it actually isn't. And we're now becoming sensitive to night or week to week changes in that night sky, and he's going to talk about that tonight. So please welcome Dr. Ashish Mahabal.
Thank you so much, Cameron. As Cameron said, my name is Ashish Mahabal. I'm a lead computational scientist here and an astronomer, and I work on the Zwicky Transient facility, a synoptic sky survey, and I'll tell you a little bit about that later. The topic of the talk today is how to catch a supernova, and it's transient friend. So you'll learn what a transient is in due time. It's not what we see outside, we see those in the sky. And the thing about this is that we have been doing it all along, but through this game that we hope to bring it to all of you. So you can also catch supernovae and other transients, and we'll try to see how. So this is the broad outline of my talk. We'll start with the changes that have happened in astronomy over the last 2 or 3 decades. Then we'll learn what a transient is. Primarily in a sentence, a transient is an object that changes in brightness in a relatively short amount of time. How much relative it is, how much it changes by brightness, those are the definitions that determine or tell us what kind of transient it is. The third thing is, that's what we'll learn. What are the different types of transients? We won't learn about all of them, but we'll learn a little bit, a few. So just to get you introduced, and then there'll be a lot that you can explore on your own. And of course, the most important thing, how to catch them. That's why we are here, right? So let's look at the changes in astronomy that have been happening over the last few decades. You know the last 3 things. The processing power of computers has been increasing a lot, yes. And then not just CPUs, but we have GPUs, which allow us to do a lot of gaming stuff, but also it allows us to do many, many things in parallel. And that's helped astronomy tremendously. And of course, the internet not just so that you can connect, but you can bring data back from the telescope easily in real time without human intervention. So when I started my research long back in India, the devices that we had to use were magnetic tapes. And the biggest data storage device that I had was 150 megabytes. Can you think of that? How much do your phones have? 1 GB, 2 GB, right? I think that's the kind of thing that we are thinking. So what I have in the table here is a comparison of 2 different surveys, both done from the same telescope at Mount Palomar in San Diego County, Caltech's telescope. So what you see on the top right are portions of photographic plates, and you can see the dates here, 1990 and 1992. So they were taken 2 years apart, same filter, and there was a slight overlap between the 2 plates, because at that time you could not have multiple observations of the same part of the sky. It was very expensive, it would take a lot. So in the table you can see that we went from photographic plates, which is what was used in the 1990s for that survey, the digitized Palomar Observatory Sky Survey. So it was done with photographic plates. 3 different emulsions were used, J, F, and N, which are equal to GRI band. These are just the separations of the electromagnetic spectrum. So our vision, we encompass the rainbow, and then within that, if you split them apart, different filters allow us to see different features in different stars. And what this allows us to do is that when you do that, one can find about temperatures of the stars, and can find out about their ages and many different things. So that is why we try to use filter by dividing the electromagnetic spectrum in general. So in photographic plates, we had an equivalent of GRI. We're using GRI in ZTF, which is the right-hand column. So from photographic plates, charge coupled devices. With DPOS, we were able to do 1 epoch each in the 3 emulsions in 15 years. So roughly 5 years were needed for 1 epoch. And with ZTF now, in 5 years, we have done 500 epochs. So you see how fast the cameras are now. Similarly, we got to 20th magnitude in 1 hour. So in the photographic plate, we had to keep the telescope open for an hour to get to 20th magnitude. What is 20th magnitudes? It's about 15 magnitudes fainter than 5th magnitude, because the magnitude scale is inverted. 5 is brighter than 20. 5 is roughly what you can see with your naked eyes. And 5 magnitudes equal to 100 times. So when you go from 5 to 20, it's a difference of 15 magnitude, which means 100 times 100 times 100. So you can see 1,000,000 times fainter than what your naked eye can see with the telescope in that amount. But it used to take 1 hour at that time. And with ZTF, you can reach slightly fainter than that in 30 seconds. So that's again another way in which the technology has changed. And of course, the last row is the biggest telling thing, right? In 15 years, the digitized portion of the data came to 3 terabytes, 1 terabyte per emulsion, 1 terabyte per filter. And now with ZTF, in 2 nights, we get 3 terabytes of data. So that's how the changes have happened. So what you see on the left-hand side here, this is the frame that ZTF covers. Again, it's the same telescope, different camera, so we can cover the same area. These are large aperture, small aperture, but large field of view telescope cameras. And that's why we can cover a very large area with, and that's why we can cover the entire northern sky fairly quickly. All right, so what this enabled us to do is multi-epoch sky surveys, and that is what opened up the time domain. So as Cameron said earlier, rather than being able to see the sky only once, we can now do equivalent of doing digital movies of the sky. So we can look at the sky again and again. That is what allows us to see how things change. So you see a sentence from Douglas Adams's Hitchhiker's Guide to the Galaxy here: far out in the uncharted backwaters on the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun. That's our sun, right? This is the Hertzsprung-Russell diagram, which shows many different properties. Temperatures are changing, luminosity is here, etc. And this is where our sun is, a fairly ordinary star. And there are many different kinds of stars. Stars sort of evolve along this sequence, but the stellar lifetimes are so long that within human lifetime, we cannot really see stars changing, right? But when you look at a very large number of stars, you can see them in different phases of their life. So you've got the main sequence here, there are dwarf stars here, there are supergiants here. So just like if you're looking at a large crowd, even a small crowd like here, you see people who are middle-aged, people who are slightly getting on with age, and children, right? Similarly, with stars, when you look at a large number of them, you find them in all kinds of stages. And that's the power of a survey. You're looking at a large number of them. So in some sense, you're looking at all of them, and then you are able to pick things from there to study. Because given how slowly stars vary, 90% roughly do not change much in the lifetime of a survey. But when you look at a billion stars, even the 10% is 100 million. So you can look at 100 million stars that are changing, and some of them, say 10 million, would be changing even more. And you can start studying populations of these objects. And that's where, again, the beauty of something like a sky surveys. And ZTF is a wonderful survey, it does lots of things, but it's not a unique survey in some sense. There are other surveys doing other niche areas. There are other bigger surveys that will be happening that have been surveying, that has been done for a long time. But ZTF is fairly powerful in terms of how much sky it can cover, how long it has been going, and that will be doing it more. So a single ZTF image covers roughly 200 full moons equivalent. That's, again, the power of that. And it can see 1,000,000 times fainter than what we can see with the eye. The eye, of course, we see 1/25th of a second. We have a 30-second exposure. So all that comes into picture. And I don't expect you to read or understand all these numbers necessarily, but I just wanted to show large numbers, right? Because we have 1 billion objects that we have been observing, that ballpark, more than that actually. And then we have 500 to 1,000 times each of them is being observed. So total number of observations is 1 billion times 1,000, right? We have a fairly large number. And then what astronomers do is that they connect CCDs and computers to the telescopes and directly take data. Very few of us would go to a big telescope and try to see through the telescope. You knew that, of course. But what I'm trying to say is that much of our dealings happen in terms of using the computers to access the data. And we have programs which allow you to just use a command line and be able to access them. So here what I show again, you can see that in the recording, you don't need to write down anything. But this is how we deal with the thing. So much of our data are online, they're public, accessible to everyone, and you can just pull whatever data that you want. These can be images, these can be time series, you can combine the data sets in different ways, and so on. So today what we are going to do is understand a few of these variable objects, transient objects. In our survey, we see all kinds of things. We also look at solar system objects, comets, asteroids, near-Earth asteroids, extragalactic objects, active galactic nuclei, supernovae, tidal disruption events. Tidal disruption events are those where what happens is that when a star gets very close to the center of a galaxy where there is a black hole, the black hole can rip apart the star. So there's a tidal disruption that happens. So we see those events. And of course, we see lots of different galactic variables, all kinds of variables. The variables include objects that are pulsating, so their size is becoming smaller and larger. We know that the sun has flares. There are solar flares. There are some stars that can have 1,000,000 times bigger flares. And of course, life may not exist on planets around those stars, but we do see these very large flares. Then the third thing that you see is just like the sun has spots, sunspots, so there are stellar spots, and those are the cooler parts of the star. And so as the star rotates, when you see the cooler part, then you see that the magnitude gets fainter. And so those are the kinds of changes that we also see. So there are many different kinds of variations. And some of these types are more frequent, some of them are more rare, and so on. So the 4 types that we'll be looking at today specifically are hosted objects. By hosted objects, what I mean is that they are in an external galaxy and we can see that galaxy in our images. So there is a host galaxy to that object. The second one is nuclear. These nuclear transients, they are also associated with a galaxy. That is, you can see a galaxy in the images. But in this case, the object that we are seeing, the transient that we are seeing, it is much closer to the center of the galaxy. So the first one, the hosted one, could also be close to the center, but more likely in this case would be somewhat away from it. An orphan transient in this case is where we do not see an obvious galaxy associated with it. It could still be an extragalactic object that is somewhere else in a faraway galaxy, but it's just that the galaxy is too faint or too small for us to see. And here what we'll be seeing is something that's suddenly getting brighter. And a variable is something that is more persistent, that we have seen it before, we are seeing it again, but it is changing in brightness. So those are the 4 that we'll be mainly looking at today. All right, so the data that we get, this is our main currency, what you see in the image there. So what we have is that this is from just a week back, 21st July. This is a 30-second image that ZTF had taken. And what we have is that because of all the past images that we have, we can compare it with older images. So this is one of the older, deeper images. We stack the images so that it becomes fainter. And you can see near the center here that you'll see an object. So when you subtract this image, the deep image from this image after proper scaling, you get this difference image. And then this object stands out. So the galaxy has been properly subtracted out and this object stands out. So that is our transient. That is the object that we are after. And this image is fairly small. It's a 63 by 63 cutout. But remember, this is our ZTF field of view. There are 16 CCDs. Each CCD is split into 4 quadrants by 4 amplifiers reading them out. So there are 64 3K by 3K images that we are getting. And so the total number of pixels is 3000 times 3000 times 4 times 16 in a single 30-second image. And we get a camera that is 600 megapixels. So again, if you're proud about your 15 megapixel camera, you're 40 times something bigger than that, right? And that is why we can see much deeper and we can see so much of the sky again and again. But this single snapshot, this is a snapshot taken a week back, right? It doesn't tell us too much. It tells us that there was something bright there. But what does that mean? Then what we can do is that because we had all these past observations, we can ask our archive, what was there before? And then this is the kind of thing that we get. This is called a light curve or a time series. On the x-axis, you see days are given. So this is when the 21st of July was. And then we ask, okay, tell us what you had before. And again, as I said before, smaller numbers in magnitude is brighter. So this is the brighter part. This is the fainter part. And roughly here is our detection limit, meaning objects that are fainter than about 20 magnitude or so, we cannot see them with ZTF with full significance. And that's why we put these triangles here, upper limits, because the object is likely to be fainter than here. All we are saying is that it's not brighter than here. It could be here, 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 anywhere down there. So when we look at our older snapshots like these and put those data together, then we see that this object has been getting fainter from here. So it had peaked about 2 months earlier at 16th magnitude. And it is about 18.7 magnitude here, 19 magnitude. So it has become fainter by about 3 magnitudes in about 2 months. 1 magnitude change is roughly 2.5 times. So 2.5 times 2.5, which is roughly 6.25 times 2.5, roughly 15. So this object has become 15 times fainter in about 2 months. And then before that, it had rapidly become brighter. So in a matter of days, it had gone from not being seen to peaking and then over about a couple of months fading away. So that's a supernova. The star explodes, becomes really bright, and then fades away, right? And so while the pictures are pretty, The real information comes when you combine different kinds of data sets. In this case, we have combined lots and lots of images, and that is what tells us about this time series or light curve. So this light curve is the real currency of many of the things that we do in time domain. And different objects will have different kinds of light curves, and that is what we can feed our machine learning algorithms to learn from. Because again, I've been telling you how big data we have, and as these data accumulate, there's no way that we or all humans on Earth can look at all these objects. So remember, I told you we have 1 billion sources. There are about 8 billion humans on Earth, and so many of them. So we are getting more and more. So with 100 points, 1,000 points, it's just going to get bigger and bigger. That's why we need to train more machine learning algorithms to do that. Okay, so we saw an example of a supernova. This is another example of a supernova. Again, you see this is a different kind of galaxy. This is a much brighter supernova now. Well, not brighter because you see it's still about 18th magnitude, but it's seen in a more obvious way compared to the earlier one because it's not so much lost in the galaxy itself. And then again, we do the same thing, subtract this reference image from the new image, and we get that bright object. And if you look at the light curve for this, again, we ask for older images, and you see that this was not changing too much, but it was also not seen before. It rapidly increased and then started getting fainter, and then it plateaued off a little bit, unlike the earlier one, which kept on going down. So in this case, this is a slightly different kind of supernova. But again, you see the same kinds of information that you have available for that. So supernova is one of the things, hosted type, that we were looking at. The second that we want to look at is nuclear type. So again, you see that there is a galaxy here, but in this case, even in the reference image, we see the object there. We don't see much of a difference between those two. And then we see that there was a brightening between the two because when you take the difference. But now when you look at the light curve, when you look at the time series for it, it's all mishmash. It was not really like how it was in case of a supernova when it suddenly exploded, become brighter, and then went fainter. So when you look at the light curve, then you can say, oh, this is again in a galaxy. This is a hosted object, but this doesn't look like a supernova. And then based on the models that we know that this is likely to be an active galactic nucleus. There is something happening near the center of the galaxy. The black hole is eating a little bit of this and that, or the accretion disk around it that's warping a little bit, or the jet that's coming out that may be flapping a little bit. One of those things is happening. We don't know exactly what unless we get more data. And that is where combining the data with other observatories like X-ray, radio, etc. can come in, or going to infrared, going to ultraviolet, etc. Various different things. But again, the point here is that this is a nuclear source associated with a galaxy, closer to the center of the galaxy, and not a supernova in this case. But you can also have supernova that are nuclear, that are close to the center of the galaxy. So that doesn't get ruled out. So there are these ambiguities that can happen, and more data tell us about these things. The third kind of source is an orphan source that we are talking about. So again, what you see is that in the reference image, you barely see something there. But then you suddenly see a very bright spot, and this is the bright spot when you take the difference that you see. And now if you look at the time series here, there was nothing for a long time. Well, this is only 20, 30 days, but there was absolutely nothing there. And suddenly there is 4 magnitudes of brightening, and 4 magnitudes is roughly about 30, 35 times or 40 times, right? So suddenly a big thing. So this is an example of an orphan object. But again, we are looking at similar kinds of things. We have cutouts, we have got light curve, and then we can get to more data. And the time series tell us about how things were before. So what we have here is a variable now. This was very persistent. We see that it's also here. To the naked eye, these may not look very different from each other. But when you take a difference between the two, then you can see that there is something there. So how we detect these transients is that all the images that we have, remember the 3K by 3K by 64, we do differencing for everything. And then within that huge data set, when we find something is changing, then we zoom in there and do these 63 by 63 cutouts. And then when we look at the time series for this, it has been going up and down. Lots of things have been happening. So these big gaps that you see between these big blobs are annual gaps. So as the Earth goes around the sun, there are times of the year when part of the sky is in the direction of the sun, so we cannot observe it. And it is these gaps that are indicated by that. So quickly, by looking at this with an optical telescope time series, you can tell that 1 year, 2 year, 3 year, 4 year, 5 year, there's roughly 5 years of data there. And what this variable was doing all along was getting as bright as 17 and going to the detection limit up to 20 magnitudes and doing that again and again. And we'll learn a little bit more detail about that later on. So this is one kind of variable that we are seeing. Here is another kind of variable. Again, a persistent source. You see them in both. When you see the difference, you have got a bright object that is seen. And in this case, there is something interesting. There are some parts where we don't see any points. What does that mean? So in this case, very likely there was rapid increases in brightness and rapid decrease in brightness. That is what you can infer from here. So again, you have object going up to 16th magnitude and going down up to the detection limit and going up and down. And this is where what we now need to do is do various other things to try to understand what this is, disambiguate with other kinds of variables, etc. So what we need to do with variable stars is try to understand whether they are periodic and how they would look. So the time series that you saw earlier, again, this was over roughly 5 years. And if you were to stretch that out and start looking at that, what we are showing here are some phase folded light curves. What that means is that we can determine what the period is using some techniques. And then we figured out that the period for this particular object was 0.15 days. What that means is that 6 times every day, it is going through this periodic change. This is a different star and also star type. So it has a period of 0.2 days. So it is doing the periodic changes 5 times a day. This one less than 2 times a day, because 1 divided by 0.6 is roughly 1.5. Whereas this has a period of 3 days. What this means is that every 3 days it is going through those periodic changes. And then there are other stars which have periods of 10 days, 300 days, 500 days, and so on. So there is a huge variety in there. And again, they come in different frequencies and so on. So how we come to these is by folding the light curve. So what happens is that this is how a typical light curve looks over 5 years. This is the RR Lyrae star, which happens to have a period of 0.6299 days. And you have to be fairly accurate there, because if you get that wrong, then the folding is going to be different. So what we do, you determine the period, you line out the light curve. This is our light curve only for that period, for 0.6 days. Because remember that we take an observation of one part of the sky every 2 to 3 days. So within 0.6 days, we are not going to have an observation every period. But we take a period, put it there, then we look at the next 0.6 days and take all the points there and overlap it with the first one. Then go to the next 0.6 days or 0.26299, take that out and overlap it with the earlier set, then the fourth, then the fifth. And in 5 years or 1500 days, how many 0.6s fit? There are about 2,000 or more than 2,000 of those. So we take these 2,000 different cuts of this original light curve and overlap them with each other. And when you do that, then you get this beautiful thing. So it has been periodic all along. It's just that from individual observation or very spread out observation, it's not immediately apparent to us. So those are the kinds of things that we are looking at. All right. I told you that I'll tell you only about 4 types. But how do we determine the 4 types? What we have are classifiers, machine learning classifiers. So we have a classifier that asks, is it a hosted transient? Another one that asks, is it an orphan transient? Third one asks, is it a nuclear transient? And sometimes, because these classifiers are independent, they can fight with each other, or more than one classifier can claim it. So we can have a classifier that's saying, oh, this is a hosted. And at the same time, for the same object, the nuclear classifier could be saying, no, no, this is a nuclear one. And when we have such ambiguity, and we can have the ambiguity because the light curves that we have are very, very sparse, then we say that it is an ambiguous source. And in this particular scenario, I'm simply calling it a wild type. And we have a couple of different wild types. So what you see here, for instance, is that this star, or whatever object it is, was getting very bright. These are again likely 5 different years. So year 3, year 4, year 5, it was showing somewhat similar behavior, getting bright. Maybe it is a long period variable where it goes up and comes down, but we are not really seeing both those phases. But look at year 2, it was doing hardly anything, and we don't know why. And maybe that is the reason that the 2 classifiers were not either fully confident or they were conflicted or something. So those are the ones, ambiguous ones, that we are calling wild type in this particular case. And there's another type that goes in there. So there's a whole zoo of transients. We saw some nuclear, some hosted, and even within variables, there are lots and lots of cases. So on the left-hand side is extrinsic variability. That is, the variability is apparent, just it seems like variable, though nothing is happening inside. The way it could happen is that, as I said, the spot on a star, it is not varying, but it's just rotating. And you can, to you, it can seem that it's varying. Or what can happen is that, again, eclipse, when 2 stars go around each other, it can seem that their brightness is varying because one occults the other and then the second occults the first. And all we are seeing from this distance is just 1 point. That could happen. And then on the right-hand side, you see intrinsic variability where you can have the pulsation star becoming bigger and smaller, or there can be eruptions. These can be smaller eruptions like stellar flares, or supernovae where they're completely exploding. So all those kinds of things, right? And then when you have additional observations with radio and X-ray, they can lead to additional windows that tell you more about these. So there's this zoo of all kinds of variables, transients. I have been studying these things for more than 2 decades. And then what happened a few years ago was this. So how many of you recognize this? You do? Okay, how many of you played Pokemon Go? Well, a few, good. So I was playing it for a few days. And of course, it was fun to do that. But what you see here is the distribution. There are commonalities that you can see with transients, right? You have some that are everywhere. Some are virtually everywhere. Some are very common. And likely the most famous Pokemon is the Pikachu, which is a special one. And then just like in astronomy, there are also some myths and some still not convinced it exists and that kind of thing, right? And then some are grass Pokemon, water Pokemon. So I thought, why not make a game like Pokemon Go, right? This thought had started long, long back, and finally it has come to fruition. So now we have ZARTH. So ZARTH is Pokemon Go, but for astronomical transients, right? And so this is the team that made ZARTH, and the ZTF team is much bigger, of course, so we take ZTF data, and Dhruv Pindawala here, he did a lot of programming, and then Thea Tumar, who was a surf student until last week, he finished the final parts of the programming and did various things with related to security. And Anika was a surf student last year, and I believe she's in the audience somewhere. You can say hi. Don't feel shy, you can say hi. So she worked on it last year on doing some sparsification with transients, etc. And the good thing is that this is based on SkyMap, which is an open source software of the sky. So you can take your phone and move it around and you see the sky. So thanks to them that we could layer something on top of that. And the one reason we don't have an iPhone version, we'd very much like to do that, is because iPhone does not have an open source equivalent of SkyMap. So if we have something like that, we'd be happy to put it. And even if no one has an open source software, we would be interested in porting it to iPhone also. So this is the Android app. And how many of you have Androids? Okay, there are a few. Good. So like in the classroom, maybe you can share your Androids with others for now, right? And so if you scan this, you'll be taken to the Play Store and you'll be able to download the app and you'll be able to go to that. And it's not sharing the screen? Okay.
Sorry, 1 second. Sorry, online audience.
All right. Then slideshow. Okay. That's okay. You just read this. So if there are people who want to use their Androids and scan this and go into that, try to download it, maybe you can help others and that'll also help you go along. Because the next few minutes, what I'm going to do is describe how to play the game. But you'll also be able to learn a few things even if you don't have an Android, and hopefully we will have the iPhone version soon. So when you log in, what happens is that you are taken to the screen and you sign in with your Google account. We don't store any of your information. Your whatever sign in you are using, email gets used, and then you select a name. Unless you choose your real name, no one will know what your real name is either. And we do have leaderboards, but on the leaderboards, what is not going to happen is that your real name won't be shown unless that is what you have used it. And when you go in, you get put into this version, this form where it is the SkyMap version. And then you choose a name the first time, and then you get put in SkyMap. And then when you touch the screen, these are the few different menus that you will be seeing. So this menu is exactly the sky map menu that was before, except for the last icon here. The telescope icon is the ZARTH icon, which toggles the ZTF transients that we put in. And every night we put in new ZTF transients. So what you will see today are transients that were detected last night. So you are really looking at the freshest set of transients. And because ZTF detects 100,000 transients every night, not all of them have been looked at by humans, by astronomers. We do have filters. The folks here who work on ZTF do go through many of them, try to looking for specific kinds of objects, and they would have picked up many of them, but not all of these would have been looked at. So there are potential very interesting objects that no one has looked at, right? And so you can move around the phone and it'll point to the sky, of course, and you should feel free to do that right now if you're downloaded the app. But also what this allows you to do, this toggles being able to move the sky with your finger. So if you don't have to look like an idiot, that's not what's happening when you do that, right? You're really being smart, but you don't know what people can think about it, right? So you can just do it with your finger and look around. And then this is the thing that we have introduced, all these menu items. This is the weekly leaderboard, the perpetual leaderboard, and then this is a guide which tells you what are the transients available today in that. And then there is a drop-down menu here that has additional things that tells you what the settings are about. There's haptic feedback, audio, and those kinds of things. There's a guide, and of course you can share, right? You can let people know that you have ZARTH and that they should have it too. And then the most interesting thing is this menu, which you have a daily credit of points, which you use to catch the transients. And then you get points for these transients. And the 4 different kinds of transients have different schemes for them. And depending on their magnitude, whether astronomers have taken spectra for them, those vary a little bit. And we have not fully revealed what it is. So one of the Easter eggs is to find out what it is and try to catch better transients than others have been catching. Because in your daily credit, you cannot catch all the transients that are available for that night. And in fact, we tell you the theoretical maximum that is available. So you can try to play against the theoretical maximum in a way that you're playing against the game. You don't need someone else to play it with. So again, we have got hosted, nuclear, orphan variables, and these are how some of them look. And to start catching a transient, how do you catch it, right? Because that's what we want to know. So you start by touching a transient to do that. And here is some example, this guide of how you go about doing that. So when you touch the transient, this is the pop-up that comes up. You're told what its magnitude is, what its type is. This is the ZTF name, the real name that we give. It's like a phone number, but people keep those in mind too. And then when you click on this button, catch, you catch it. That's it, right? If you don't want to know anything else, that's all you do. You find transients, touch them, this pop-up comes up, catch them, and you keep on climbing on the leaderboard. But if you're more curious, you'll click on this more info. And when you click on more info, this is where that brings you to. And I lied a little bit. This is not exactly what we show to all our ZTF colleagues. They, as I said before, can access things directly from the computer. They don't get told what the cost and points are, for instance, because that's for the game. And you can hear that this is a variable and that's a variable. But this variable, and it's increasing in brightness all along for 5 years, it has becoming brighter and brighter, though it has some excursions to the faint end as well. But it has a cost of 5 and you get 140 points. Whereas this one costs 75 and you get only 180 points. So that's how you can decide which one you should get, which one you should not get, and so on. And this TNS, that's a transient naming server that tells us how many spectra astronomers have taken. If astronomers have taken more spectra, it should be more interesting and you get more points. So that's one of the ways to figure things out. And then we use the magnitude, rarity, etc. to figure more things. And of course, you can use the share button too. So from the second pop-up too, you can catch it. Or if you click on the share, first it catches it, adds it to your leaderboard. And then you can share it on wherever, X, Twitter, Threads, WhatsApp, mail, whatever, right? So that's the primary thing. You can touch it, catch it, and keep on going with that. And then this is how the weekly leaderboards go. For each of them, you have 10 different people that are shown. And we'll be starting to put this on the website soon, hopefully in a couple of days. This app is very fresh. It was released on 12th of July, so only about 2 weeks back. And it's not even been advertised to all the world. Not even all astronomers know about it. It'll happen slowly, hopefully, soon. And this is how you can get to your collection. What is your collection? The top 10 are seen again, when it was caught is seen. And the light curves get added to your gallery. So you can revisit them, you can share them later as well. And this is how the set of transients for a given day is shown. This is from yesterday. So typically the wild types are very few, 1 or 2 wild type 1 and less than 10 wild type 2, and the others tend to be more. And this is the theoretical maximum that you can reach with those points. So these are the broad features of the game. There are fresh ZTF transients available every day, refreshed at UTC 0, which happens to be Pasadena 5 p.m. currently. So every day at 5 p.m., new transients get put in. Light curves and images are available in-game, as I just showed you. Transients are ranked by how rare, important they are. It's slightly subjective, but that's something that you can figure out also. You can compete with others in getting all these points. There are weekly and overall leaderboards. The weekly leaderboard resets at 0 UTC on Saturday. That is between Friday and Saturday. Again, 5 p.m. on Friday, that is when the weekly leaderboard resets. So if you are logged in now and if you see only a few people playing, that's likely the reason, because until 5 p.m. the weekly leaderboard was also full. And then types of transients, there are 4 major ones and the 2 wild types that we have, and max points per day are shown. Daily credits 2,000. Within that you cannot catch everything, but you can try to maximize by trying to optimize your catching strategy. There are many technicalities that I have left out, but we can discuss that if you're interested. So we're using Firestore database as the backend. The sparsification of transients to choose few from ZTF's 100K. As I said, we have 100K transients every night, and we put at most 200 because we don't want your phone to be just a mismatch of transients, right? That would be horrible. So we pick at most 200 into these 6 categories and put those on. The algorithm to determine points for a given transient, algorithm to calculate max points achievable. That itself is a very interesting algorithm. So it should be a fun thing. And the role of spectra that have been taken for these. So many things that I have left out. There are many educational possibilities with this, of course. This is only an outreach thing right now. We are not demanding anything back from you when you play the game. It's pure outreach. But you can clearly do citizen science with this, because especially with the wild types, trying to understand why 2 different classifiers are claiming them is a thing that's interesting to us, important to us. And internally, we are trying to solve that problem, trying to understand that better. But if you want to give feedback, that will be very helpful. And of course, what teachers could do is that introduce this in their classroom, and they can have their students learn about one type of transient 1 week or 1 month and go to the next one next month, have them look at the different light curves and images, etc. There can be group competitions with that and so on. So here is an example of one of the other wild types, for instance, doing rather wild swings in some of the time from that. And then future possibilities. One can add other surveys to this also. So it doesn't have to be only ZTF, because the mechanism can be used for other surveys quite easily. Additional types of transients could be added. Within the variables, as we saw, there are many subtypes. One could in principle go to those subtypes. And of course, we'd like to develop it for iPhone too, if possible. This is a new app. It will improve. It likely has a few bugs too. If you find any bugs, we'd be happy to learn about them and try to improve that. You can find more details at zarth.caltech.edu. or reach us at one of these 2 email addresses that you have. And there are additional Easter eggs, something of this kind that you are free to discover and have fun with. And I'll stop with that, and I guess we can take some questions.
Questions from the audience? Yeah.
Thank you. That was really interesting. I was wondering why you chose your like the avatar for the guy.
Sorry?
I was wondering why you chose that avatar for the game.
Okay. So we're trying out a few of the AI tools to create that, and we're trying many different prompts. And when it came up with something that looked funky, but with also all these nice things added to it, we liked it, and that's how we decided.
Other questions from the audience?
Yeah, can you tell us? Okay. Can you refresh my memory where you got the science photo and where you got the reference photo? Where are those 2?
Oh, the reference and the science image?
Yeah.
So the science image is from last night, typically, meaning every night. So ZTF survey has these 30-second cadences. So we are on one part of the sky for 30 seconds. That's where we get our 600 megapixels. Then we move to another part of the sky, another 30-second exposure to cover those 200 full moons of equivalent. And the reference images are also from ZTF. So all past images of the same part of the sky, we stack them together so we get a very deep image. And that's why we subtract. And that is why in the deep image, you don't see something, but in a shallow image, you see something that must have really brightened up. That's what our transient is. We also look for the other way around. So if you had something bright earlier, but it has faded, we also look for those two.
Other questions?
Easy question, but when you put up the magnitude of 16 and 18 and 20 and how it oscillates between the magnitude, is that apparent magnitude or what we see from the sky right now?
So it is an apparent magnitude in a specific system that we have. So what happens is that the numbers that I mentioned before, that with the naked eye you can see about 5th, 6th magnitude. So it's roughly in the same system. And that is why with 20th magnitude is what you can go down to with ZTF. Yes. So it's not calibrated to the distance of the object from us.
Oh, another question. I think the dog has a question too. I didn't even know there was a dog in here. It's a wild place here.
How are you getting to, with 30 seconds, right, getting to magnitude 20?
Sorry, in 30 seconds?
In 30 seconds of exposure time using charge-coupled devices, how are you getting to magnitude 20? And you're saying that the aperture of the instruments that you're using aren't that big, right?
It's a 1.2 meter telescope.
Oh, okay, so it is big.
Yeah,
Oh.
it's fairly large. Yeah, it's not small. It's not as big as, say, the Keck telescope, but still sizable.
Maybe one last question before we go to our intermission. Any? How many people downloaded the app? I saw a few people playing it. Nice, nice.
So you should
online
catch
audience.
transients, and then you'll
Catch
be on the
transients.
leaderboard. So,
Yeah.
so one thing that I didn't say, and that if you don't find a transient by just moving around, there is a lens button. If you type T next to it, then it'll take you to one of the transients. It'll direct you in that direction.
I have a question. I think there was that variability slide, and there was intrinsic and extrinsic, and I think I saw one that was a combination of both, at least one. Do you mind expanding on that? How it could be both? Or is that really two, the BY?
I think these are separate in this case, yeah.
Ah, they're
but
separate.
both are red dwarfs.
Okay, so they apply
Yeah,
to
so
like
the
same
broader
type of star.
category, yeah. And yeah, there would be commonality, so yes.
Thank you.
Though I'm not an expert on that, and I don't know the very specific in case there are some aspects of one and the other that may be common to both types.
Okay, let's thank our wonderful talk from our speaker. Thank you, Ashish. So now is the portion of the evening where we kind of split, and you can go between the different parts. In about 2-3 minutes, we'll set up a table here and start a Q&A panel consisting of our speaker, myself, and 2 other members of the department to answer questions from the audience on the topic of the presentation, on astronomical transients, but in general on astronomy and physics. You'll get your chance, sir. And at the same time, we're going to set up, the telescopes are set up just in the fields behind me. You can go out there and you can go back and forth between the two. If everyone rushes out right now, then you'll have to stand in a line waiting for the 3 telescopes. But if you phase in and out, feel free to do so. We'll be on the telescopes until about 9:40, so you got about an hour. And then we'll be in here until about 9:50 or maybe 10 o'clock. So, yeah, choose your poison. See you in a bit.
Again, wonderful. These are just like the top of the line, man. Yeah, we've gone through other and you're like, you put on the best stuff. Oh, really? We have to get to know the Comic-Con too. I think that
I was excited to see your
we were sold out, man. We were like, we have to turn people away. And the audience was very receptive. really nice. The questions they ask are phenomenal, and all of the
Amazing. Well, that's great. Yeah, I'll.
I think Clifford knows Kip's board, and he wants to get him.
Oh,
I
that'd
don't
be
think he's
amazing.
ever heard a Nobel Prize winner. But yeah, next year let's. I'm gonna have you guys also suggest a panel for you guys too. Absolutely. Okay. Yeah. Take care.
Yeah, we can use both of them. I look like I fooled someone at least. That's true. They're looking for more. They're not doing it.
I got more telescopes on. I never got. It's literally.
Oh, because there was no one there yet?
Going back and forth. Like 3-4 revolutions through.
I don't want to bug in there, so
A little bit described.
Okay.
Sorry, spoilers.
So what is it that I ate? No, so on the magnitude, how did I see the objects that say were bright in 80 magnitude, 60 magnitude, and 20 magnitude? Why is if it's supernova, I remember the magnitude of too far away. I don't think they said it wasn't polarized. It was still less. Well, that's what I thought. That's not what I thought. I meant by its, yeah, I already asked I got really weirded out when someone said, just because it's a super huge, super giant, blue giant supernova doesn't mean it will be a black hole. And somebody said actually that just because it's a bigger supernova doesn't mean it's a black hole. There's sometimes smaller supernovas that are black.
All right.
And bigger ones.
Thanks to everyone for sticking around. We're going to get started with our Q&A panel. And essentially how this is going to go is each of us will give a 1 minute or so introduction to who we are and what sort of science we work on. Of course, we're happy to handle whatever science questions you have thrown out there, and we can try and address them as best as we know. But we're all human. We all have a finite knowledge base. And so we're going to be able to better answer questions relevant to our specific expertise. So I'm Dr. Cameron Hummels. I am a research scientist here, and my focus is on computational modeling of galaxies and the regions around galaxies and the larger cosmological volume that extends out to the edge of the universe. So I can answer questions on, those things, and then just random other stuff too.
Hi, I'm Samantha Wu, or Sam. I'm a fourth-year graduate student here at Caltech in astronomy, and I work on theoretical astrophysics, so like theory behind stars and stellar evolution, and like the theory behind some transient events and that kind of thing.
My name is Ashish Mahabal, and I'm a research scientist here. My thesis was on radio galaxies, in particular their infrared and optical observations. And I've been working on sky surveys for more than 2 decades now, so a lot of observational stuff, but I've been moving more and more towards computational stuff. And I also do methodology transfer to other areas of science, like early detection of cancer, for instance, but we'll talk about astronomy only today. So, but surveys, I've been working on many different surveys, and that's, in some sense, I had to worry about all kinds of objects because we want to classify everything. And then I work with all domain experts in different expertise. Like someone asked a question about specific stars, I can go and ask that to someone else and try to incorporate that in the classification processes.
And machine learning. He works on machine learning too.
Hi, I am Kaustav. I'm a third-year grad student in the astronomy department here. So I work on exploding stars or supernovae, which Ashish talked about earlier. So these are basically stars which explode when they die. I study them using the Zwicky Transient facility primarily, the instrument which again Ashish talked about in his talk. And I'll just leave you with a fun fact about supernovae. So a lot of the elements that we see around us, like for example, zinc or silver, possibly even gold, were first formed in some exploding stars. So a lot of the atoms that form you or that you see were possibly first formed in an exploding star or supernovae.
All right, while I fiddle with this microphone and replace the bad battery, are there questions from the audience on whatever? Maybe something you read in the news about physics or astronomy, or something that Ashish was talking about? Yeah.
My question is actually more about just the data, the amounts of data that were in the presentation are just massive.
They are.
And they're daily. And so who's keeping this? How is that keeping, like, who owns that? Who manages that? And who dictates who has access to that?
Sure. Excellent question about who holds on to the data, how does it get processed, how does it get reduced, how does it get stored? This is a problem in all quantitative sciences with the advent of computers and supercomputers and these instruments that generate so much information. And Ashish is going to solve it for all of us here.
Yeah, of course, that's a huge problem. And in radio astronomy, for instance, they don't need to keep all the bits. They can derive certain outputs from their data, and they're happy with that. But even that is big. And as you heard from ZTF, if it's roughly 1.5 terabytes every night, and we have been going for 5 years, it's petabytes of data. For now, it is stored at IPAC, which is a part of Caltech. But when we write proposals, then say NSF funds us, they tell us that, yes, you can store the data, there is some funding available for that. But what happens after the project gets over? And that's becoming a bigger and bigger problem. So NASA tries to have mandates for the NASA observatories, but that's something that we do need to solve together. In fact, just yesterday was the deadline for special sessions at the next American Astronomical Society meeting, which will be in New Orleans. And we put in a proposal to study exactly that, trying to get more suggestions on how we can go about doing that. Because even the photographic plates, there is digitization that has been happening for that, and that's being stored, because that's the best archive that we have for some very long-term variables, but that's getting much worse. So what we also want to understand with CCDs, it's going in the opposite direction. We are generating so much data that not all data are being looked at. And so we need to have meaningful ways of storing that and meaningful ways of being able to use that. Most of us have been going after low-hanging fruit because there are so many of those too. And what we really can do with these large surveys is start to understand about families, about populations rather than individual objects. That's slowly starting to happen, but that problem is recognized. I don't think we have a proper solution yet, but for the current surveys, we try to maintain the data as best as we can. For the previous ones, we at least try to maintain archives or some abstracted versions of that in the best way and try to combine it with newer surveys, because that's very important. Only partial answer, sorry.
Additional questions from the in-person audience? Okay, there's a question from the online audience. We can go back and forth too as the night goes on. So you showed these light curves, how different objects are changing in their brightness over time. And obviously you can use this as to classify it based on its existing behavior, but are there other ways, perhaps including machine learning or even not machine learning, anything that's predictive that allows you to predict how that object is going to change in its brightness in the future? And do we do that?
Yeah, so for instance, based on the knowledge that we currently have, one can build models, and the models can be used to try to extrapolate the light curves, whatever sparse light curves that we have. And there are other methods like Gaussian processes where what one can try to do is try to interpolate between the light curves to the best of our knowledge. And in fact, the wild type 1 and wild type 2 that I showed, those are ambiguous classifications. So one of the ways to do things is say that if I assume that it is one of those two and there is a model for each of them and try to predict at different times how they would look, and then pick a time when the two models predict something different, and I do an observation at that time, then that is going to disambiguate the observation for me. That's going to disambiguate the type for me. So that's been thought of, but it's not always very practical to be able to organize observations of specific ones at the same time if you're thinking of an entire sky survey. But for a smaller set, that's typically what's done.
So the predictive power also slightly depends on at what phase of the transient do we catch it in. It's something like, say, if I give an analogy for humans, it's like I can look at a teenager today, and then 1 hour afterwards, I can predict that he would look something similar, but they would change a lot. But probably if I look at someone who's a bit older, and then if I predict how they would look and not predict a lot of changes, that would most likely be true. So I think it's similar for transients. So it depends on which phase of the transient do you catch it in. So at times they tend to change a lot, and that's kind of harder to predict. At times the behavior is very predictable in the sense that I can look at it how it behaved 3 days before, and I can predict how it would behave 3 days after.
Just following up on that, are there tests to see how well you were able to predict the behavior of this based on a machine learning algorithm, and how accurate are they? Because I imagine some stuff is predictable. It gets brighter, it gets fainter, it gets brighter, it gets fainter on a really regular periodic basis. But then, there are some objects where it's like cruising along, it's not doing anything, and then it explodes like a supernova, and it may be very difficult to predict that.
Yeah, so there are validation sets for known types of objects, but especially for the objects that are not regular, it's very difficult to do that. So I showed one example of a flaring star, and a flaring star typically would flare once in our lifetime. So it's not doing anything and it suddenly flares, and that can be something, the signature can look initially exactly like transients we are interested in. There are so many flare stars that there are few people, of course, interested in that, but most transient people are not interested in flare stars. But those are things that keep coming in. So there are predictive models, and most of the times for reasonably behaved sources, they work well, but not always. And even in supernova, there are subclasses where it can look very different, and that is what really drives the science. Do you want to add anything to that?
Yeah, I think, again, the success of the predictivity probably depends on, as Ashish said, the type of the transient, and secondly, again, the phase of the transient. So it can be very good at predicting what it is just based on even just pure science and not using any machine learning at all, because we just understand the science of the transient so well that we can actually predict exactly how it would behave even a year from now. But again, there are some transients and certain phases where we just are horrible at it.
Questions? Yeah, I don't mean to hog the mic, even though I have the mic.
What parts of the world are these telescopes located in, and can you tell us about the telescopes that are gathering this data?
Go ahead.
So this is the distribution of the telescopes, right?
Where are they, and why do those make good locations for observatories?
Right. So my talk was for ZTF, which is Palomar Observatory, not far from here in San Diego. That's a great location. But earlier bigger telescope was Mount Wilson, not far from here. And if you try to observe from there tonight or right now, because of the Los Angeles sky, we cannot do much. And so that is why what astronomers try to do is that try to look for areas which have dry weather, non-humid, and maybe even above clouds, so trying to go up. So Chile, for instance, has many peaks of that kind. Similarly, Hawaii has good peaks. And so there are a few distributed areas that are there. And that's how things get picked. For instance, some Chilean mountains have lots and lots of telescopes, mainly for that reason. Then you have got very good observing sort of 365 days. Maybe you're able to observe 300 days. India, where I come from, because of monsoons and various other things, there are not too many good sites where you can have too many nights. But even there are telescopes coming up in Hanle now in the northeast. There are telescopes high up. So.
Yeah, really one of the keys, there's a few different keys. One is you don't want to be near a city because there's a lot of light pollution, obviously. That's the most intuitive thing, I think. But then, yeah, mountains are good. Dry environments, because it reduces the amount of cloudy days that are going to block you from seeing whatever you're trying to see. But also, yeah, the moisture in the air, not just because of the cloudiness, but because it can absorb certain wavelengths of light that we might want to see. So it's not so important for taking images, but when you're taking spectra, where you're breaking down the light into various different colored components, you'll get some absorption at certain wavelengths, certain colors that get blocked because of carbon dioxide or water or methane that's in the atmosphere. So you want to minimize that. And you can do that by getting higher and higher up. But one thing that's a little bit more subtle is the idea of, it's called seeing, astronomical seeing, and that is the amount of turbulence in the air overhead. So, when you're out, actually, we have a good example on this field. If you've ever observed, or you go out tonight to look on the field, often things on the western horizon, there's a power plant on campus, and it has these fume hoods that spit out all this hot air. And when you look through that, it's like looking through a mirage in the desert, because the light refracts through the different turbulent layers of air, and it refracts and it causes things behind it to twinkle. Now, twinkling stars are great and all, but they're not really great for astronomers because it causes the object to move and to dance. And that's not what you want when you're taking, if I try and take a picture of a friend in the dark and they're moving and jumping around, it's going to be all blurry. And the same is true for a twinkling star. So you want places to set your observatory where the air is going to be calm and that atmosphere is going to be calm, so you don't have that turbulence. And that tends to be like the western sides of certain continents, like the Andes Mountains in Chile, or the Hawaiian Islands, because the air is coming across the ocean and it's not being perturbed by any land masses, and so it remains calm. So, yeah.
One follow-up question.
Oh, yeah, here.
Don't worry about it.
No, because the people online can't hear the question, and then they'll be confused and shout at me. So.
Simple question. What percentage of the sky do you have access to?
Right. So from here, for instance, what we can do is that we can see the pole star when you go out. And so that's 90 degrees clearly in declination, and you can see either side of it. And then we can go south to about -30 declination. So in that sense, we have access to about 2/3 of the sky from here, right? And that's typically true for most parts of the Earth. So if you are in the southern hemisphere, you'll have access to the southern pole, but not all the way to the northern pole. So that's roughly what we can see. But the important thing also is that when you're looking close to zenith, you have the least amount of perturbation happening, and that's the best seeing. So as you go in any direction away from zenith, then the amount of atmosphere is being added. So the perturbations because of that increase. And that's called the air mass. And as the air mass increases, your observations tend to get blurry, worse. And so even if you have access to 2/3 of the sky, you try not to use all of that.
I made a crummy illustration. I'm not a very good artist, but I tried to. So in line with what Ashish just said, very plainly, we're here in the northern hemisphere, like 30 or so degrees latitude. And so from here, we can essentially pretend now we're on the horizon here on the edge, and we can see this tangent line that goes over the North Pole, so we can always see the North Pole in the northern sky and then down here, but we rotate around. So we can see like all this part of the sky, but we can never see down here from our location on the Earth. But somebody else down in the southern hemisphere might be able to do the same. But at any moment in time, we can only see what's on our horizon. So it takes the rotation of the Earth that helps with that. Yeah.
You spent about a minute describing a process for inferring the period of a rapidly rotating object from a large number of sparse samples. And you put a lot of work into it, and I did not follow it. Is it actually, I mean, computationally, what I would do is simply generate 1 million possible periods and try to curve fit them all and see what fit the data. But could you try to explain again exactly how you infer the period of a rapidly rotating object?
So 1 million would be rather large if you want to do for everything. And as I showed, the accuracy that we want should be good. So for instance, if I have something that is half a day period, and if I have 1500 days, and if I get it off by a small fraction, then the number of periods that fit into that long period means that every time I'm off by a little amount, but that mounts up. And then when that happens, then I'm not getting a good period at all. So there are alternate methods also. And so yes, I did not do perhaps a fast enough or quick enough job, or rather good enough job. So again, so what we had was points. This is how, suppose the curve is. If you had continuous observations, then you can immediately see that it is in fact periodic. But if you do not have that many observations, then what you would typically have is at 1 point here, 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 etc. And so you can use several different methods that are approximate. Loam-Scargill method is one of the methods that is used well. So Fourier transforms are used, and those are the ones that, so you figure the period out. And once you have figured that out, then what you do is that if this is the period, then these are the cuts that you would do. And then we fold the period. So you take this portion, put it on that, take this portion, put it on that, take this portion, put it on that. So even if I have only 1 point in each of these bins, when I put those 1000 or 500 or 100 bins together, then I get a reasonable semblance to a periodic light curve. But yeah, so Fourier transforms is one, then we use some entropy-based methods, etc. to do that.
Additional questions? It's okay if you don't have any. As a follow-up on the question about seeing different parts of the sky, there's an online member who asks, what are the benefits to sending a telescope to space? And obviously in space, you aren't confined by these conditions that we talked about with light pollution or turbulence of the air because you're up above that. So it's a good place. It's just expensive to send telescopes to space.
So that's obviously the thing, that from space, you do not have the turbulence in the atmosphere. So that's fantastic. You can have very tiny pixels. So I did not mention of the pixel size. So at ZTF, we have pixel size of roughly 1 arc second. 1 arc second means 3,600th part of a degree. And the moon is approximately half a degree. So if you were to divide the diameter of the moon in 1800 parts, that's the resolution that we get with ZTF. But then if you go to Hubble Space Telescope, the resolution of Hubble Space Telescope, which was launched almost 30 years now, roughly. So it had a resolution of 0.1 arc second. So 100 HST pixels could fit into 1 ZTF pixel, right? And it was not a survey telescope. HST would take pointed observations and get data, and you could send that back. One of the troubles with something that's space-based is right now we do not have very good methods to send the data back to us. So there is another observatory, the TESS observatory, which in fact is a survey observatory. And there it accumulates a lot of data. And while the data can be good, because it's doing a survey of the entire sky, the pixels there are very large. So just like 100 HST pixels can fit into 1 ZTF pixel, more than 100 ZTF pixels can fit into 1 TESS pixel. Because what they want to do is that they want to cover a large part of the sky. And so many times in a single pixel, you can have more than 1 star. And then you want to try to disambiguate that. So yes, benefit going out, seeing excellent, but data rates high and not easy to transfer it back here.
So You talked about some of the different kinds of things that get brighter and fainter in the night sky. And one thing that I was curious is, we know about supernovae, exploding stars, but there's a different kind of exploding star that actually Sam talked about at a presentation about a year ago. They're called tidal disruption events, where stars get too close to a black hole and they get pulled apart because of the extreme gravitational forces close to that black hole. It's pretty magnificent. But how are those different, and how do you measure them differently based on their brightening and fading relative to another exploding star like a supernova? Is there a signature that you can say, well, that thing got bright and then it got really faded really quickly, or it got bright and it took a long time to fade? How do you distinguish between these objects?
I think, so as Cameron mentioned, so the tidal disruption events are caused by big black holes at the center of the galaxy. So if something is not close to the center of the galaxy, it's not a tidal disruption event. So that's like the first big check.
So like proximity to the center of the galaxy. If it's not close, it's definitely a supernova.
Yeah, it need not be a supernova,
Okay.
but
it's not a tidal disruption event.
Yeah.
Okay.
So that's the first cut. Secondly, we know what elements are present in a supernovae versus what elements are present close to, say, what are the possible elements that are present in a star that's disrupted by this big black hole. So there's something called spectra. So just like what Ashish mentioned about having this broad filters, where you have like an integrated light from a certain wavelength to a certain wavelength. What a spectroscopy does is that it's basically like how a prism splits white light into 7 colors, but the spectra that astronomers use, they're kind of like prisms, but then we look at finer wavelength cuts so that we can know which elements are present in each of in the area in the point that we are pointing at. So the spectrum is kind of like a fingerprint of each element. So I can look at the spectrum and say that, look, there's helium present in it. I can look at a spectrum and say there's calcium present in it. So based on the elements that are present, for example, in tidal disruption events, helium-1 is an expected thing, and you expect them to be at a certain velocity. For example, if it's 10,000 kilometers per second with like a nice looking absorption profile, then it's not a tidal disruption event. But if it's like you have some helium-1 at around say 6,000 kilometers per second or lower than that, it could be a candidate TDE. So there are also the light curve at times also. The light curve alone can also be used to separate between a supernova and TDE at times. But then again, there are some objects always which are there, which you just cannot differentiate at all. There'll be those annoying ones where you spend months trying to figure out what it is. But yeah, I would say out of 10 events, almost for 7 of them, we can tell them apart, but probably for 3 of them, we are not sure.
I would also just add, I think if you look in different wavelengths, you can also distinguish, because for tidal disruption events, it's a lot of energy because it's like being disrupted by a black hole. So you're more likely to have bright features in like the X-ray, or like if you look in those very extreme wavelengths for counterparts to say like some sort of optical observation, that's also a signature of whether it's going to be like a TDE, something that went through something that's so extreme that you can get that much energy to produce X-rays, versus like for, I don't know, just like a regular supernova, it's not as common to have like a lot of X-ray observations, I think. Yeah.
So basically what we're saying is if it was a supernova, there's going to be a casket, and if it's a tidal disruption, it's going to be more of a younger star being, oh, no, I'm not ready to go.
I guess younger is kind of a relative term. I guess the stars that are disrupted in a tidal disruption event, it can be any star technically, but the most common types of stars around the galaxy now are stars closer to the mass of our sun, and those are actually quite old because they live for a very long time, versus supernovae, type 2 supernovae, come from the deaths of very, very massive stars, more than 10 times the mass of our sun, and we see them explode because they don't live for very long. They live for millions to tens of million years, while our sun is going to live for billions to 10 billion years. So I guess in terms of their actual age, supernovae are actually from younger stars time-wise, but it is true that TDEs are happening to stars that were not necessarily supposed to die yet. So.
Yeah.
Well, you talked earlier about the ideal locations for telescopes and conditions in those locations. So the highest points above sea level on the surface of the Earth are in the Himalayas, but I'm not aware of any noteworthy telescopes in the Himalayas. Is that because it's just too dangerous? I mean, so there's the Andes are one thing, but you have to find like a happy medium between as high as you can go and too low. Is it just too dangerous to get to build something up there?
It can also be very unpredictable there in many cases. So snow avalanches. So every day, for instance, when hikers also go up, there are times when they cannot be doing that. And there are phases, even daily things that can be happening there, the snow melting, etc. that's happening. So I don't know all the exact reasons, but yes, above a certain height, it becomes too dangerous. Also for oxygen levels that we can sustain, it becomes impossible. And Hanley, that is mentioned, is roughly in that direction. So one of the Indian observatories. So Himalayan, not exactly, slightly higher than foothills, not just foothills, but that would be the primary thing I would say. Do you have anything to add?
Yeah, I mean, I agree with that. I mean, I think it is a challenge to get up to high elevations beyond what we're able to at 18 or 19,000 feet in the Altiplano in Chile, and going up to into the Himalaya up to like 25,000 feet. I think to build infrastructure at that elevation is extremely challenging. Sure. Well, and in fact, a lot of the observatories, the highest elevation observatories, will have the observers' quarters having oxygen pumped in to it, because otherwise it's just too challenging. Even with Keck telescopes and many of the other telescopes at the summit of Mauna Kea, there are restrictions on how fast they allow you to go up to, astronomers are like, oh, we're scientists, we have to go there and we have to get it done and then we have to go home, and it's all a big rush because we're all busy. Everyone in the modern world is so darn busy. But anyway, so you go there and they're like, no, you can't go up to the summit too quickly. You have to hang out at 8,000 feet just to acclimate before they let you go up to 14. And at the summit, you can only stay for a certain period of time because they don't want you to get acute mountain sickness, elevation or altitude sickness. And so there's all these restrictions because otherwise it's problematic. But I think the ALMA telescope, the submillimeter telescope that exists, that's it. I think it's like 18,000 feet. And so oftentimes the observers don't actually go to, and in fact with Keck now too, Keck, there's an observing facility in this building where you can go and essentially network in via the internet and see cameras of the operators who are there, who are at the telescope, and they do a lot of the manipulation of the telescope, and you just interact with them in a room where you pretend you're there. I mean, that was done before COVID, but now it's done even more because COVID restrictions, people couldn't go to the telescope, but they still needed to use the telescope. So there are the possibility of doing these remote kind of things, but you still have to build a telescope in a really challenging environment, which is hard. So, yeah.
So I have like a general science question, might be a bit subjective, but for the whole panel, do you feel it's possible and we'll be able to see within our lifetimes the Big Bang, the first, big explosion?
Who wants to talk about cosmology and see the Big Bang? There are reruns of it on yeah. Big Bang theory, yeah, exactly. Who wants to talk about this?
Okay, seeing as you said, it's subjective, and I don't understand exactly what you mean. But one way to look at Big Bang is that Big Bang is when space and time also got created, as to the best of the theories that we understand right now. And so the Big Bang happened everywhere in the universe. It happened here because everything was together, right? And so this is where Big Bang happened, and we are sitting right there right now. But seeing, one way we talk about things in astronomy is that when we say that a certain object is, say, 70 light years away, what that means is that it took 70 years for the light from there to get to us. So we are seeing back in time that way. right? And so one way to look at it, maybe if we know the exact age, then if we are seeing an object that's far out. But again, coming back to what I said earlier, because everything was at the same location, you cannot really distinguish between that.
One thing I'll just add on that. So, because I think I know where you're going with this, because oftentimes you'll read an article in the news that James Webb has now seen objects at the edge of the universe that are only 200 million years after the Big Bang, or 150 million years, or 100, it's going closer and closer to just after the Big Bang. And so the question is like, when will we actually be able to see like the Big Bang itself? And, Ashish is correct that we won't actually be able to see the Big Bang itself, but really where's my fancy pens? Well, that's just it. Part of it is the opacity of the universe. So I'm going to erase my wonderful blue globe here. So we're here, and I don't know why I drew us as a star. I should have drawn us as we're the Earth here. Here's my wonderful little Earth, and as Ashish pointed out, the farther away things are, the more it takes time for those signals of that light or gravitational waves or anything to travel from those objects to us. So let's say Sam is 1 billion light years away. So it took 1 billion years for that light to travel to us. And yeah, let's say Kostov just said he's the Big Bang. So he's way out here, and Ashish is in between. So the farther away we're seeing, and of course the light is fainter because it's traveled more distance, and it becomes more challenging for us to see it. We can see farther away, but at some level, there's kind of a boundary about how far away we can see. And that is because in the very early universe, just after the Big Bang occurred, the universe was extremely dense.
The whole universe was in a hot, dense state.
The whole universe was in a hot, dense state. And because remember, the universe is expanding. So as it expands, it's been effectively cooling off because it's been spreading out. But in the very early moments, it was extremely hot and it was extremely dense. And it was so hot and it was so dense that light rays, photons, were flying around and constantly slamming into other light rays and getting absorbed, or light rays weren't running into other light rays, they were running into other particles. And so you'd have, for instance, a hydrogen atom consisting of a proton and an electron that were orbiting around it was orbiting around the proton, and one of these light rays would slam into it because it was so crowded in there, it had nowhere else to go, and it would ionize that. It would kick off the electron from the proton, and then they'd be flying freely. And eventually that electron would get close enough to another proton and settle in and make another happy little atom, but then it'd get slammed by another light ray, and it would break it apart. So this is happening constantly all around the zone. And it basically means that light can't travel more than a few skips before it runs into another atom. And at some point, the universe finally expanded enough that those photons were no longer energetic enough, because as it expanded, the photons lost a little bit of energy. They were no longer energetic enough to break apart those atoms that were forming. And that's a moment, it's not really a moment, but a period in time that people refer to as the surface of last scattering. That's that was the moment, we'll say moment, but it wasn't really a moment, the moment at which those photons no longer were running into the atoms or had enough oomph to break apart the atoms. And then they could just kind of fly freely wherever they were going. That was about 300,000 years after the Big Bang. And those photons have been flying kind of freely ever since. But because the universe has been expanding since then, those photons have been expanding and stretching out their wavelength. So initially they were in the UV part of the spectrum at that surface of last scattering. And since then they've been expanding. They went into the visible part of the wavelength range. They went into the infrared. And right now they're almost into the radio. They're in what's known as the millimeter wave. They're millimeter. Oh goodness. CMB, they're microwave, forgive me. They're microwave, and it's known as the cosmic microwave background, the CMB. And you can find pictures of this because scientists have studied this, and it basically shows like how far away we can see. We can't get all the way to the Big Bang at Kostov. We can get just past Ashish. We're stuck. We're stuck at this distance of 300,000 years after the Big Bang. That's the farthest we can see. There are other constraints that essentially prevent us from even getting that far, but that's kind of the maximum that we can get to. So we'll never actually be able to see the Big Bang.
Thank you.
Yeah. Sorry, that was very long-winded.
Related to this kind of, so let's say there's an object that is 11 billion light years away that we can see with the Webb telescope or something. That's how long the light took to travel to us. But the universe has been expanding the whole time, and the width of the universe, breadth of the universe, we want to put it, it might be like 90 billion light years. So how do those values relate to one another? When we say that something is 11 billion light years away, how does that take into account the fact that the universe has been expanding the whole time? And, you know, is there a formula where you could say that, well, this object plugging in the cosmological constant would be actually in reality this far away if it still existed? Or
that is an excellent question. You guys want to talk about light travel distances and expanding universe? It's not a simple formula. That's the point. You can look up, there are a number of cosmology calculators you can find online that essentially do this in the background. And I can't speak for you guys, but whenever I have to figure out the distance to one of these things, I don't do the math. I go to one of these cosmology calculators that, and you effectively plug in, like, you can plug in the redshift at which something is, you can plug in the time after the Big Bang at which something is, and it will tell you, but you make a perfectly reasonable statement. So if light got emitted at Ashish, let's say, we'll say it's traveled 10 billion light years to us, but the thing that emitted that light, Ashish, because the universe has been expanding, is way out here now, and it's like 40 billion light years away from us instead of the 10 billion it was when it emitted that light that traveled to us. So yes, you are right. The universe is larger than just the age of the universe times that distance in light years, but there's not a trivial, nice little equation that will spit out the answer of that light.
To be clear, I asked if there was a formula. I didn't ask if there was a simple formula.
I'm sorry, there is a series of equations that you can solve, usually numerically, that will allow you to do this, but it's dependent on the cosmological parameters that you assume, like the amount of matter or the amount of radiation or the amount of the cosmological constant, which is dark energy, which describes the accelerating expansion, and all of these together will allow you to figure that out. So it's dependent on all of those, which is one of the other reasons that it's not a trivial thing to do, because we don't know specifically all the values of those equations. Okay. Sorry. Let me see. Are there more questions? I can see what our online audience has in questions too, but I give you guys precedence because you guys are here.
Thank you for the talk.
Oh yeah, sure. Yeah, check out the telescopes. Yeah, if you want to check out the telescopes, get out there ASAP, because they're gonna shut it down in the next few minutes. How many elements heavier than helium formed in a supernova? Or like what elements heavier than helium formed in a supernova?
I think the question is which elements form in a supernovae which are heavier than helium. Okay.
Here's a related question. Do you get the formation of elements in a tidal disruption event where a star gets too close to a black hole and gets shredded? Does that cause nucleosynthesis? Does it cause the creation of heavier elements? Or is it just in the cores of stars and binary neutron star mergers? And
so I would think, so for the first question.
Sure, yeah, sorry, I didn't mean to complicate things.
So how elements are formed, I think the question was after helium. So the story of element formation is that we know that the sun is converting hydrogen into helium. And once it's done, it would continue doing that for another 5 billion years. And once that's done, then it would start converting the helium to a bit higher elements like carbon, oxygen. And then that step usually goes on depending on, and how far along that goes on depends on how massive the star itself is. So for example, if a star is very, very massive, say around 10 times or 20 times the mass of the sun, it would keep on producing heavier and heavier elements till it reaches iron. So iron is the 26th element, as in it has 26 protons in its nucleus. So the reason it cannot go above iron is that, so we know that we get energy from the sun, and the reason is that as it converts from hydrogen to helium, it releases energy. But once it has to, basically it's how it produces helium is that you fuse together 2 hydrogen atoms. And if you remember, both these hydrogen atoms have positive charges. So they don't actually want to come together. So you need very high energy and very high density conditions for them to actually come together and fuse into helium. But once that process happens, a lot of energy gets released, which we call the energy from nuclear fusion. But what happens for iron is that there's no more stable nucleus than iron. So if you want to try to form an element which is even higher massive than iron, you'd actually need to give it energy. So that process actually does not happen inside the bellies of the stars. So, but we do have heavier elements on Earth, right? We have gold, we have, well, calcium is technically lighter than iron, but there are lots of heavy elements that are very abundant in the Earth that we see. And very good location. I say that to produce heavy elements, you need very high temperature and you need very high density so that you can get this very positively charged nucleus bound together to form heavier and heavier nucleus. And if you have recently watched Oppenheimer, you understand how complex that whole process can be. So a very good location for getting high temperature and high density are supernovae explosions. So these are very, very, very highly energetic processes. So just to give you a sense of the number, so sun has been burning for 5 billion years and would continue to burn for another 5 billion years. And the amount of energy that it would release in this whole 10 billion year lifetime, a supernova explosion releases the same energy in a few seconds. So you can understand how energetic that is. So in this supernova explosions, all kinds of different elements are formed, including calcium, including iron, including zinc, possibly gold. But we feel that gold is something which is produced by some other kinds of processes, which are merging neutron stars, but I can probably speak on that for another half an hour. So yeah, I guess that answers the first part of the question. Regarding the TD nucleosynthesis.
Yeah, just if a star gets too close to a black hole, does it, and we know it leads to an explosion and a brightening on the sky, but does it also lead to the synthesis of heavier elements?
I mean, I'm not sure, but my guess would be no, because the brightening happens because as the star gets too close to the black hole, it's disrupted and it forms an accretion disk around it. And it's this accretion disk which results in the brightening and fading of the transient. So
just because it's super hot.
Yeah, but I don't think the high density, high temperature conditions required for the nucleosynthesis of heavier elements are actually met there.
Okay.
Yeah, I think it's ironically the opposite because the star gets torn apart. So then it actually, I was just talking about this before I saw you today, actually.
Oh, perfect.
It was like, we were looking at it and it looks like the star gets less dense because it gets torn apart and what's left is puffed up. So it's actually creating a lower density environment. And the star usually was only like using hydrogen in the first place anyway, so it just becomes less dense.
I see. So the core of the star is super dense and super compressed, and that keeps it, fusing hydrogen into helium. But then it gets torn apart, and then it essentially puffs up and it gets hot, but it's not compressed by the gravity in that accretion disk. Okay, interesting. Cool. Thanks, guys. Yeah.
You all studied transients and supernovas for quite a bit. Do you personally have a favorite supernova in history?
Favorite supernova? 1987A. I don't know. That's hard. The one that went off in the Pinwheel Galaxy a couple months ago was pretty cool. What was that? 2023 IXF? Yeah. I could see it last week observing. was still visible. Because it's like 14th magnitude or something, 13th. I don't know. Do you guys have favorites?
The only one I remember is 2019 DGE. But yeah, I don't remember any other names.
Okay, okay. Yeah. My comment?
It's not my favorite supernovae, but it was a supernovae explosion happened, which happened in 1054 AD.
Sure.
So there are paintings where there are two suns on the sky. And the reason is that that was a supernovae which actually happened in our galaxy. And it was so bright that people could see two suns on the sky. And when we look at it now, after 1,000 years, we see that there's a huge ball of gas because the supernovae ejecta mass basically expands at speeds of 10,000 kilometers per second. And if you give that, multiply that by 1,000 years, you have a very nice looking picture that if you search something called Crab Nebula, then it's a really pretty looking picture that came out of a supernovae, which humans could actually see and documented 1,000 years back.
So there's a online question from Slovakia. My question would be, how long does it take for a supernova to explode? I mean, the initial explosion. Not, I guess not the light curve.
I'll answer the question in 1 second. The answer is 1 second.
So that's 1 second from which it starts to get bright until it reaches full brightness, or 1 second for the collapse, or? Okay.
A star is a star because there's two fighting forces going on here. It's like a tug of war. So the whole star is, say if you consider you are present at the outside of the star, so there's gravity which is pulling you inward, and there's gas pressure which is pulling you like outwards. And that external radiation pressure comes because of this fusion process that I mentioned about earlier. And the sun is at a process where this tug of war is currently balanced. So gravity equal to radiation force. But once we stop fusing hydrogen, then we would no longer have that outward force to deal with the gravity. So everything would start collapsing. And if you give it, I won't go again into the detail of the process, but once you run out of this inner energy processes that actually can give this outward force, what you are just left with is gravity. So it just takes a few seconds for the gravity to collapse the entire star. And then what happens is that it's like if I throw a ball very hardly at the table, it would rebound. So it's something similar happens in a supernovae. So all of the external material falls inward, but then it can only fall inward beyond a certain density. And once that high density is reached, it basically rebounds off that very hard surface. And all of that process is 1 second. And then the supernova that we saw that Ashish showed the nice light curves, they can last for hundreds of days.
I'll just say that, like you mentioned, is it the time to the peak? So it's not the time to the peak because even though what Kasif described happens so immediately, the energy of that has to go out to the surface of the material that's like surrounding that explosion. And that time scale is controlled by how fast photons can move through the material and get to the surface, which is usually on the order of like days. And so that's why in all the ones that she showed of supernovae, the time from like the lowest to the peak was about days in most of the supernovae, and that is like the typical time scale for that energy to get to the surface. But there is like an initial flash that we often don't see. Yeah. But I mean, for you to see that, you would have to like know that you were going to look at the supernova.
So one of the things that I was going to mention is exactly that. What is happening with these time domain surveys is that earlier you would find a supernova because it has become brighter. So typically an amateur astronomer would find that something has happened, and then you try to find all observations that different observatories may have taken to try to piece together the puzzle to see whether you can find something during the rising time. But because of surveys like ZTF, you find them routinely that you can find them while they're rising. But even before they start rising, it's likely that some bumbling, or flash is happening. And in order to catch that, we will need to have, because those will be very short-lived also, we'll need to have more continuous observations, which it's not possible right now. As I said, we take one snapshot every 2-3 days typically. And so for the progenitors, we may need to be looking at them or keep on looking at some areas again and again in order to find that.
Additional questions? There was a question on here asking about the 26 billion year old universe. So I don't know if you saw, but last week, if you typed into Google, how old is the universe? It gave you the incorrect answer because it said that it was 26 billion years old. Yeah, because there was a paper, kind of a controversial paper that was published last week, and it got picked up in press releases about, I actually didn't read the paper. Did you guys read the paper? It was something about tired light, the idea of tired light. I think it was effectively that the universal constants that we assume and we've measured near us might not be true throughout the rest of the universe. And so you might have different fundamental constants, which might lead to like slower light travel time. Although the speed, relativity says the speed of light is constant regardless of your frame. So I don't know how light works. But anyway, the point is we have pretty good pieces of evidence from several different independent channels that suggest the age of the universe is about 14 billion years old, or 13.7, or plus or minus. And this paper came out saying it was double that. And so because there was a press release in the way in which Google and other search engines generate their answers to questions that you put into the search engine, if you asked how old the universe was, it was gathering that information and using that to give you the wrong answer. And a bunch of astronomers got really cheesed off at this and wrote to Google and said, you better fix this. And they fixed it within like a day, but for a very short period. But I don't think anybody except the authors, maybe even the authors don't believe this, that is actually the answer about the age of the universe. There's a lot of different pieces of evidence that suggest like 13.5 to 14 billion year age for the universe.
Speaking of wacky claims like that, what did any of you have any thoughts on this latest Avi Loeb story about meteor spherules found at the bottom of the ocean that he claims are alien technology? Did any of you see this story or have any thoughts on it?
I have opinions. Do you guys have opinions? Did you read this? There was an article in the New York Times in the last week.
Oh, no, I just meant to say I have lots of opinions, but off the camera.
Yeah. Well, but that's consistent with that story. So if you read, there was a New York Times article that's all about these various claims. Just to give some background, try and give the most objective background that I can here. There's a scientist named Avi Loeb. He is the chair of the astrophysics department at Harvard, very established scientist, very established department. And his background primarily is in cosmology, studying the nature of the universe and the age and the evolution of the universe over large scales of time. He's a good guy. But in the last few years, well, throughout his career, he writes lots of papers. They tend to be papers putting out different hypotheses, some of them kind of oddball hypotheses, but I think it's important to put these kinds of papers out to suggest creative and paradigm shifting ideas, even if most of them end up being proven wrong. But it's just, outside the box kind of papers. But in the last few years, he's been particularly obsessed with the idea of extraterrestrial civilizations and aliens, which, it's interesting, but it's not really his area of expertise based on being a cosmologist. And he put out a book a year ago or so about the search for life in the universe, primarily prompted by this study associated, you guys have probably heard about this interstellar asteroid named Oumuamua. And it was this object that was the first kind of confirmed object to have come from outside of the solar system into our solar system from deep space. And it's very peculiar because it's this slab that has it's very flat in one direction relative to the other two, I think. I don't think it's like a spear. I think it's like a slab, like a pancake. And it's weird. We all get that it's weird, but most scientists have been looking for, invoke aliens or a deity or something to explain this, some sort of normal physical explanation for this. And it's been very challenging, absolutely, to come up with this. But that's how science is. You discover something, you don't know what it is, and you search for explanations that are consistent with the natural laws. And if there aren't, then you have to invoke, change in the paradigm. But there have been a couple of viable explanations for this, and he has essentially gone and invoked that it's extraterrestrials, that it's a ship, and these sorts of things, which it's okay to invoke those things, but you really have to exhaust all the other things that you have at your explanation before you start to say, it's aliens. And most recently, no, please, Ashish, go ahead.
Go ahead. I can do my plug later.
No, I mean, I don't go on these monologues here. It's not the greatest thing.
Yeah. So in speaking of things like that, I would like to make a plug. There is a group at Caltech. We come together and write science fiction. I write science fiction too. And recently we published a book. All the authors are from JPL and Caltech. And it's called Inner Space and Outer Thoughts. If you don't have a copy, please try to get one, because there you'd find more bona fide stories, and they're called science fiction.
Do you talk about Oumuamua, the interstellar? Oh, well, okay. That would be the place for that. Yeah. Well, so anyway, this New York Times article then goes on. Avi recently had an expedition in the South Pacific off the coast of Papua New Guinea, outside of Indonesia, where he basically tried to recover things from the seafloor from a meteor that exploded, I think it was 2019, or it was in the last 5 years. And if you look at the data associated with this meteor, shooting star in the sky, it looks like it was coming at a speed and a trajectory into the solar system that would have come from outside the solar system. And although the data that we have on that are not super clean cut, so plus or minus, it could be associated with something that came from outside the solar system, but he set off on this expedition and trolled the ocean floor looking for recovery from this particular object. If it were to survive, because not all meteors end up depositing a meteorite on the surface of the Earth, but his claim was, let's look for something. And they recovered a bunch of small metallic spherules, little beads almost on the ocean floor that were iron that they could pick up with their magnets. And I think he's thus invoking that it's some sort of alien artifact associated with this. But just because something came from outside the solar system doesn't mean that it's like an extraterrestrial intelligence source and civilization and technology. So I don't know. The article, I think, did a pretty decent job of describing the general take, and you heard just now that no one really wants to engage with Avi on this from within the astronomical community. And it's not so much that we're a bunch of closed-minded jerks who just hate the idea of aliens, it's that we're scientists who are intrinsically skeptical about claims that are made. And the first thing that you try and do is be your biggest critic and guess all the natural explanations that could occur for something before you start invoking supernatural explanations. I go home and I'm at home and the light turns off when I'm at home. I don't jump to the explanation that a ghost turned the light off on me. I think maybe there's a short circuit in the wall, or maybe there was a power that went out. I'm sorry, I'm not trying to be a jerk, but but we come up with normal explanations for things, and you have to exhaust all of those things before you start to invoke crazy stuff. And it doesn't seem like he's taking that same path, which is unfortunate, especially because of his role as a very high-powered astronomer in a very high-powered department. Clickbait loves it, and I'm sure he's selling a lot of books because of it. And no offense to Avi, I think Avi's a good guy, but I think he's gone a little too far on this. And I think a lot of astronomers would yeah, it's publicity, that's right. And I think a lot of astronomers would join me in this, and that's why there hasn't been a lot of pushback officially from astronomical people in the community, is because no one wants to be on the record as going against Avi. And I'm not willing to take on that role. I don't think I just did, but people just don't want the conflict.
The camera just went
The camera went off?
No, it just went to static. Harvard
Yeah.
yeah.
Alien attack. So, any other questions? I don't know. I've been fielding a lot of questions from friends and colleagues who've been messaging me and asking like,
At Avi Loeb fan asks.
who've been asking about, there was a press or a congressional hearing a couple of days ago about some whistleblower within the government claiming that there are aliens that were, discovered and have been kept under wraps since the 1930s or something like this. And I basically have said the same thing. Like, the person is offering no evidence. They're saying, oh, I was there. It's my word. It's my word against like everyone else. Like, sure, it's possible that there are aliens out there, but let's be skeptics. Let's put on our scientist hat and require extreme evidence for the conclusion of extreme claims. And that yet has not happened. That doesn't mean that those things aren't true, but you can't just trust some dude who says he's like ex-military and he knows some people who saw aliens, like whatever. Like, you can't trust that. Trust it when you show stuff. That's how science works. I know it's ridiculous. I'm being ridiculous, but this is how it is. So.
This might be broadening.
Yeah, sure.
Some of you may be familiar with the author Bill Bryson, who writes, kind of very general in terms. And in his book, A Short History of Nearly Everything, he opens with a very interesting idea. It's like, if there's nothing else on TV, you can always watch, if you go to a channel that's very staticky, which is hard now because we all have such high definition things. But still I don't know if he said it was like background radiation. We were talking about it earlier from the Big Bang. There's nothing else on TV. You can still watch a tiny little bit of the Big Bang. Now, is that background radiation coming through, or like how would you more like define what is actually in the fuzzies? That's very broad.
That's fine. I think it is CMB. I think it is the cosmic microwave background, that radiation, this stuff that came out of the surface of last scattering just after the Big Bang. It's flying around, it's everywhere, it's hitting us on all sides because it's basically everywhere in space. And I think that does interact with the signals that we receive in our TV antennas and such. And some of the static that you'd see or some of the static you hear when you chime into between radio stations is coming from this radiation. Okay. Let's see if Avi got pissed off and wrote on our YouTube channel. I don't think so. Okay. There was the question, what's the name of the science fiction book, again, that you suggested? You've got the mic right there, Ashish.
Inner Space, Outer Thoughts. Inner Space and Outer Thoughts.
Inner Space and Outer Thoughts. And the name of the group?
TechLit.
TechLit. Okay. Yeah, there were a couple of questions about that.
And there are some famous science fiction authors who are Caltech alumni. Larry Niven, S.B. Divya, David Brin. So they have also contributed.
Oh, David
to
Brin? Really?
Mm-hmm.
Oh, that's cool. Interesting. Okay, well, it's been late. We've talked about aliens. I don't think we've ever talked about aliens here before. First time for everything. Thank you guys for joining us, sticking around for a couple of hours. Hopefully you learned something with Ashish's wonderful presentation. Hopefully you guys got a chance to check out the telescopes as well and see some of the cool stuff that's up in the sky. Just a reminder, our next one of these is a Spanish language one about stars by Dr. Rocio Quiman, which will be on the 18th of August. And the next English language one will be the week after that, on the 25th, about clusters of galaxies and their mergers, the most explosive explosions in the universe since the Big Bang. And finally, our next Astronomy on Tap will be Monday, August 14th, featuring talks on cosmic neutrinos, these lightweight particles that are flying all over the place, and remnants of various different explosions around the universe and what we can learn from them, as well as 21 centimeter cosmology, studying the early universe around Ashish here for our model, in radio wavelengths of light and what it can tell us about the early universe before stars and galaxies formed. So thank you guys for sticking around, and thanks to our speaker and our Q&A panel, and have a wonderful weekend, everybody.
And don't forget to play ZARTH.
What'd you say?
ZARTH.
Oh, I play ZARTH. Yes, of course. I'm sorry.